we've got the history of the universe to complete in one class, so we better get started. Obviously, we have to be selective in what aspects of cosmology we're going to discuss. I'll briefly summarize the standard model of cosmology without going into the details of why, or at least not all the details of why it is the standard model. Then we'll say something about Robertson-Walker. And then some explicit Einstein equations, which involve Friedmann models. If you like, roughly speaking, this is kinematics, and this is dynamics. So this will be some rather general remarks that don't depend on the details of Einstein's equations. And then we'll focus on those specific predictions that do. So the currently, and again, this is just a paradigm. It doesn't mean it's the right theory, but the current paradigm for cosmology is the lambda CDM model, where lambda stands for cosmological constant. And CDM stands for cold, dark matter. And we'll be talking about, this is sometimes called dark energy. The US has a Department of Energy. Someone suggested they needed one, a Department of Dark Energy, but they haven't got that yet. And it's sometimes called the standard model. And cold, in this context, means non-relativistic. So not photons or neutrinos or gravitons, but massive things. And it seems it explains, or is compatible with, shall we say, with varying degrees of, that's not exactly the same thing. It explains some things and is compatible with others, I suppose. But the cosmic microwave background this is the background that was discovered by Penzias and Wilson in 1960s, and is what you'd expect to see if the universe began with a hot Big Bang. And that is the incorporated into this model that there was a hot Big Bang. You want to explain why the galaxies are the way they are. It's compatible with that. There's also the abundance of light elements. the light elements being hydrogen, helium, deuterium, lithium, and the acceleration of the universe. Now, what are the ingredients? One is what's called the cosmological principle. Which says that the universe is homogeneous and isotropic. At least on large scales. Homogeneous means it doesn't matter where you are in the universe, it looks the same. Now, of course, on small enough scales, we know that isn't true. In the solar system, it doesn't look like when you're out of the solar system. But if you go on sufficiently large scales, the universe looks the same wherever you are, and it looks the same in whatever direction you look. And we'll give a mathematical meaning to that in just a few moments. Dark matter which of course no one has seen directly, but which is needed to account for galaxy rotation. And gravitational lensing that's been observed but can't be explained if you don't have dark matter. This is where light is bent not by the sun, but by a galaxy between us and the source of the light. And as we'll see in a minute, in terms of the amount of energy that makes up the universe, and I'll justify this equation later on. The total energy density being 1, most of the energy density is coming from the cosmological constant. It's about 0.7. The rest, there's a negligible amount from radiation, which I won't bother to write down. The cold dark matter is about 0.23, I think that's 0.73, which we haven't seen. And the matter, you, me, the stars and galaxies that we see, everything that we used to think was the whole universe, is a mere 0.04. So we are a sort of insignificant afterthought in the big picture. So, as I said, it incorporates the hot Big Bang. Now, it also incorporates the idea of inflation. And inflation says that at some very fraction of a second after the Big Bang, the universe underwent this gigantic expansion by 27 orders of magnitude. So t is approximately 10 to the minus 29 seconds. Now, why do people like inflation? Well, the problems in explaining the universe if you don't have inflation, like the horizon problem, the flatness problem, the homogeneity and isotropy of the universe is hard to explain if the parts that are obeying that principle were causally disconnected. And that would be the case were it not for this gigantic expansion. And the gigantic expansion also explains why the universe seems flat, spatially flat, that is. And after this inflation, it remained hot for several 100,000 years, which is, of course, a blink of an eye in cosmological time. And it's this that we see. It's the remnant of this hot period. The radiation emitted during that period is what we detect as the cosmic microwave background. And it incorporates the Friedmann-Robertson-Walker picture that I'm going to tell you about now. So let's go backwards now and talk about number one, the so-called cosmological principle. What does it mean mathematically? It's a hypothesis that all positions in the universe are equivalent. So it's the opposite of anthropocentrism. We are not special. understood in the same sense as the gas. So it does not apply, in other words, what we mean by that is it does not apply in detail, but only on the large-scale structure. What you might call a smeared-out universe. And to give it a number, you mean averaged over cells of 10 to the 9 light years. We live in a solar system lives in a galaxy, so that's not very homogeneous or isotropic. And the galaxies are in clusters of galaxies with space in between, so neither is that. And this clusters of galaxies are in superclusters and so on, so it goes. But if you get to sufficiently big size, it looks smooth, even though it may not be on smaller scales. So mathematically, what does that mean? It's possible to define a cosmological time t such that the properties of the universe depend only on t. So in particular, the density, temperature, curvature, are the same everywhere. And depend only on t. Which is the same as spatially homogeneous and isotropic. And we encapsulate this cosmological principle with the Robertson-Walker metric. This is the most general spherically symmetric homogeneous spacetime. I'm just going to quote what it is without proving what that. So in coordinates t, r, theta, and phi, ds squared is minus dt squared plus r squared of t dr squared over 1 minus k r squared plus r squared d theta squared plus r squared sine squared theta d phi squared. R of t is some as yet unknown function of time. Which we're going to fix later using Einstein's equations, but for the moment it's just some unknown function. And k is a constant. Which by suitable choice of r is normalized to be either +1, 0, or -1. 3 possibilities. And this is known as the Robertson-Walker metric. So let's talk a little bit about this metric and what it means. Well, let's just focus on the spatial part for a moment. This three-dimensional subspace, the spatial subspace. Let's denote that metric with a superscript 3. Then the RR component looks like r squared of t over 1 minus k r squared. Theta theta component looks like r squared of t. And the phi phi component looks like r squared of t sine squared theta. So you can compute the three-dimensional curvature scalar using this three-dimensional metric. And we denote that by k of t. capital K. Distinguish it from little k. And this is and I think the convention is a minus sign, little k, r to the minus 2t. Actually, let's adopt a convention where that isn't. We don't really need it. So let's look at this in the case k equals plus 1, where k is that little constant over there. Then the 3gij is the metric on a sphere. Of radius r. So in that case, space is finite but unbounded. And you can show that the proper circumference L is just 2 pi r of t, and the proper volume which is the integral d3x times the square root of the determinant of the three-dimensional metric is 2 pi squared r cubed t.
What do you mean by proper circumference?
I mean the integral. We define line, surface, and volume integrals. If we do the appropriate line integral with the right factors of square root of g and so on, you will find 2 pi r of t.
Does the proper circumference, does the adjective proper...
I guess it's the distance. It's the distance you travel on a geodesic. You go around the sphere, great circle. So when k equals plus 1 at least, r is the radius of the universe. Now, that's not the case for k equals 0, k equals minus 1, because the volume is infinite. So, r is not the radius of the universe in the same sense as it is when k equals plus 1. So for k equals plus 1, it's a sphere. For k equals 0, it's a plane. And for k equals minus 1, it's a hyperbolic surface. Now, if we take the coordinates we've chosen, these, are so-called co-moving coordinates. And physically it means that r, theta, and phi are constant for typical galaxies. And t is the proper time told by a clock at rest. In any typically freely falling galaxy. In other words, the xi equals constant trajectories are geodesics. Now, one way of envisaging this is like you have a balloon and you draw a grid on the balloon, and the galaxy here, here, and here. Now, as you blow up the balloon, as you inflate the balloon, the grid will grow, but the galaxies will stay where they are relative to the coordinates. The galaxies will not change. So go up one more dimension, and that's what the universe is doing.
Excuse me? Is there a relation between this proper time and the universal time you mentioned earlier? What is the universal time?
Can you just remind me where I mentioned universal time?
Sorry, cosmological time. I misspoke.
Yes, this is the cosmological time.
Okay, so the same thing.
Now, this also has consequences for how do we describe all these galaxies? We describe them by a fluid with pressure P and density rho. And what it means is that rho and P will depend just on time and not on r, theta, and phi. So we're going to look at the T mu nu, which is rho plus P u mu u nu plus P g mu nu and the cosmological principle says that T naught naught, or is just rho T, Ti naught is 0, and Tij is just the three-dimensional metric times P of t. So rho and P only depend on t. That's the important ingredient. So what does conservation say? And I leave you to work it out. The mu equals 0 component says r cubed of t times dp dt equals d by dt r cubed of t times rho of t plus p of t. Now, how do we get information? On this R of t. It's clearly an important question. And this brings us to galactic redshift. Let's put ourselves at r equals 0. Which is just a convention. We could put ourselves anywhere since the universe is homogeneous and isotropic, but let's choose us to be at r equals 0 and consider a light signal which obeys ds squared equals 0 equals minus dt squared plus r squared of t dr squared over 1 minus k r squared. And we fix theta and phi. Now, suppose the light is emitted at t equals t1. And observed at t equals t2. Actually, Weinberg calls it t0. Then t0 the integral from t1 to t0 dt over r of t equals the integral 0 to r1 dr square root 1 minus k r squared, which equals sine to the minus 1 r1 if k equals plus 1. It equals r1 if k equals 0, and it's sinh to the minus 1 R1 if k equals minus 1.
Is R1 the location from which the light was emitted?
Yes. Yes. Now the next crest leaves at T1 plus delta T1 and arrives at T0 plus delta T0. That also equals the same integral. And since R of t is effectively constant over the period of the light signal, we find that nu naught over nu 1 is delta T1 over delta T naught is R of T1 over R of T naught. So there's a shift in the frequency depending on the radial coordinate capital R. And now we can introduce a redshift parameter. Z, or Z if you prefer. Which is lambda naught minus lambda 1 over lambda 1, which is R of T naught over R of T1 minus 1. And if it's greater than 0, lambda naught is greater than lambda 1, and that's a redshift. And if it's less than 0, lambda naught is less than lambda 1, and it's a blue shift. And a redshift means that the universe is expanding, and this one means it's contracting. Now, what we observe, of course, is that the universe is expanding, and we can get a handle on R of t by studying the redshift of distant galaxies. Now, this dates back to the work of Hubble, who studied distant galaxies and concluded that, roughly speaking, the further away they were, the faster they were going. To see this, let's look at R of t as r of t naught into 1 plus what we're going to call h naught t minus t naught minus 1/2 q naught h naught squared t minus t naught squared. So we're doing a Taylor expansion. And what's h naught? Well, t naught is the present time. H naught is defined to be r dot over r evaluated at the present time. And that's called Hubble's constant. And Q naught is defined to be minus r double dot times r over r dot squared evaluated at t equals t naught. And this is called the deceleration parameter. I suppose it was for historical reasons that they called it a deceleration parameter and put a minus sign there, because we now know that it's negative and that the universe is in fact accelerating. So, put it another way, z equals h naught into t minus t naught plus 1 plus q naught over 2 h naught squared t minus t naught. I'll give you the experimental values for h naught and q naught in just a few minutes. But the interesting thing is that the universe is not only expanding, but the rate of expansion is getting faster and faster. So this is the kinematics, if you like. This is the framework that we want to work within.
Is the energy conserved in the expanding universe?
Is energy conserved? That's a difficult problem. Because energy in general relativity is a funny concept. You can't define it locally, you only can define it asymptotically. And if your space isn't asymptotically flat, that creates even more problems. So what is true is that the energy momentum tensor has vanishing covariant derivative. That's, when we talk about energy conservation, that's what we mean. But it might not be the naive interpretation of energy conservation. Yeah?
Didn't Boyle, Gould, and Bundy argue that matter could be appearing to stabilize their model, and we just wouldn't be able to tell because of the amount of matter that would be appearing?
Yes. Before the Big Bang became popular, there was a rival theory known as the steady state theory, put forward by Hoyle, Bundy, and Gould. And they said that the universe is expanding. Sorry, the universe is not expanding, but there's continual creation, that atoms of hydrogen or whatever are just popping into existence every now and then. Their model was very popular, and there was very bitter rivalry between Hoyle and other astrophysicists in Cambridge at the time, which eventually ended up with him quitting, going off somewhere else. But the truth was that their model was not sustainable, because when the cosmic microwave background was discovered, that was more or less very strong evidence in favor of the hot Big Bang. And their steady state model fell out of favor. In fact, it was in a radio interview that Hoyle dismissed the rival theory as though that Big Bang, he was speaking contemptuously. And that's how the phrase Big Bang was coined, by Hoyle dismissing the rival theory as the Big Bang. So it was also theoretically very shaky, because it relied on things popping into existence for no particular reason. Now you could say, but what about the Big Bang? Didn't that pop into existence for no particular reason? That's a good question. But it was hard to write down a field theory, a consistent field theory that accommodated this continuous creation of the steady state model. So it was on shaky ground theoretically, and it was eventually discredited observationally. I remember once being in a restaurant in London, and I can't remember for whatever reason, we started talking about the steady state theory. We started talking about Hermann Bondi. And after a few minutes, we glanced over and noticed he was sitting at the next table. Okay. Friedman models. Now we're going to impose Einstein's equations. Now let's first of all recall what this says. There's d by dt of r cubed rho p plus rho is r cubed dp by dt. Or you can rewrite that as d by dt rho r cubed equals minus p d r cubed by dt.
I thought we saw that when we were considering a galaxy in particular.
I'm sorry?
I thought we saw that when we were considering a galaxy in particular.
We're looking at the universe as a whole, treating the galaxies as a gas, not an individual galaxy. And we're treating the gas of galaxies as a perfect fluid with pressure P and density rho. Now we put in the Einstein equation. the naught equation and the ij equation. The naught equation says 3r double dot is minus 4 pi g rho plus 3p r plus lambda r. And the ij equation says r double dot plus 2r dot squared plus 2k equals 4 pi g rho plus rho minus p r squared plus lambda r squared. Or eliminating r double dot, you've got r dot squared plus k equals 8 pi g rho over 3 r squared plus lambda over 3 r squared. Now this has a name. This is called the acceleration equation. We can use one and two to rewrite this as r dot squared plus k equals well, I don't need to do that. I can define rho tilde to be rho plus lambda over 8 pi g. And p tilde to be p minus lambda over 8 pi g. And if it's convenient sometimes to do that, because then I have r dot squared plus k equals 8 pi g over 3 rho tilde r squared. So I just absorb that into there. And I can put tildes on there without changing it. So this is called the Friedmann equation. And these equations and these are not independent. Once again, the Bianchi identity relates them. So you can pick any two of them depending on your problem you want to address. And then finally, we need an equation of state which usually looks like P equals omega rho, where omega equals a constant. This is just an assumption, by the way. It's never been clear to me why it's such a popular assumption. I guess it seems to work, but that's what these models assume. So let's look at some examples. Let's look at radiation this corresponds to T mu mu equals 0, lambda equals 0, in which case P is 1/3 rho, so omega is 1/3. Matter which is sometimes called pressure-free matter, is sometimes called dust for historical reasons. But it has omega equals 0, and we'll put lambda equals 0. And then vacuum energy in which rho equals a constant, omega equals -1. Equals minus P. Well, actually, I've jumped the gun a little bit. P equals minus rho. Now, if I plug that into this equation, you can read off how rho depends on R. And in this case, rho goes like R to the -4. In this case, rho goes like R to the -3. And in this case, rho is constant. Generically, rho goes like R to the -3 into omega plus 1. So this tells you some important properties of the universe. This will dominate when R is small, which is early in the universe. This later in the universe. But the ultimate fate of the universe will be determined, will overwhelm. Eventually this will overwhelm these. And this is the kind of universe we'll be in. Now, there's something called the critical density of the universe. Well, a critical density which is such that if the density of the universe were greater than the critical density, the universe would carry on expanding. And if it were less, it would collapse. And this critical density rho sub c is 3h squared over 8 pi g. Now h, don't forget, is changing in time. What we call the Hubble constant is this time-dependent function evaluated at t equals t0. So the critical density is also changing with time. And it's also convenient to define omega to be the density over the critical density. So it expands if omega is 1 or greater than 1, and contracts omega is less than 1. Now we can write the Friedmann equation as minus k equals r squared h squared into 1 minus 8 pi g rho over 3h squared minus lambda over 3h squared which equals r squared h squared into omega into 1 minus omega matter minus omega lambda. Well, actually, this is rho matter plus rho radiation, both. So we could put in another term for the radiation. And don't forget, rho, omega is going like one over r to the fourth in the case of the radiation, 1 over r cubed in the case of the matter, and constantly in the case of lambda. Now, observationally, what kind of universe are we in? And what seems to be the case is that we're in a k equals 0 universe with lambda greater than 0. If lambda were less than 0, you can see from these Friedmann equations that the universe would eventually collapse. Whatever the value of k. Sometimes people talk about k equal plus 1, 0, and minus 1 as open, flat, and closed. And if there weren't a cosmological constant, k positive means expansion, k 0 means expansion, and k negative means contraction. But if there's a cosmological constant and it's negative, the universe will collapse anyway for any value of k. But that's not the universe we live in, apparently. The universe we live in is one with k equals 0 and lambda greater than 0. So let's look at Friedmann's equations. Let's solve those equations in this case and see what we get. So r dot squared, this is our universe, is 8 pi g over 3 rho matter times r squared plus 1 over 3 lambda times r squared. And the solution is r equals r naught rho m over rho lambda. Rho m, capital M, is rho little m at t equals t0. That's the convention. Times sine to the 1/3 square root of 3 lambda t over 2. And so T naught, from this we can calculate the age of the universe. Is 2 over 3h omega lambda to the half tanh to the minus 1 omega lambda to the minus a half, where omega lambda is lambda over 3h naught squared. Yes, that's an h naught. So if we plug in what we observe for the density of the universe, we find this is about 13 billion years. Which is, actually it's 1.3 times 10 to the 10. And what we find is that omega is approximately 1, with omega lambda being the dominant and most of that is cold dark matter. We account the visible universe is only about 5% of the total, which is a rather humbling conclusion to the lecture course. Any questions?
So do you think that delta is the cosmological constant or is it dark energy?
Okay. I've made an assumption here, which some people might query, that the origin of the dark energy, the 0.7, is a cosmological constant in Einstein's equations, which corresponds to the omega equal -1 equation of state. That is the most conservative, simplest explanation for dark energy. There are rival theories of dark energy, like quintessence and things like that, which I haven't mentioned, but I can't say they're not right because we still don't know enough about the universe to be able to say. But the paradigm, the lambda CDM model that I mentioned, assumes that the dark energy is Einstein's cosmological constant. Any other questions about anything?